Good morning, everyone, and welcome to the JKMRC Friday Morning Seminar Series. On behalf of the University of Queensland and Sustainable Minerals Institute, we'd like to acknowledge the traditional owners and custodians on the lands on which we meet today. We pay our respect to their ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize their valuable contributions to Australian and global society. And for this seminar, it is my pleasure to welcome Dr. Stephen Morrell. Steve majored in metallurgical engineer at Imperial College in London from 1977 to 1980 and spent the next 7 years gaining practical experience working on African mines before moving to Australia and completing Masters and Doctorate thesis in grinding, mill simulation, and power draw modeling at the JKMRC. Employed at the JKMRC from 1989 to 2000, Steve led research projects such as Amira P9, as well as HPGR, fine grinding, and mine-to-mill comminution programs. In 2000, Steve started his own consultancy, and a few years later founded SMC Testing to license the SMC test. So today, he'll be presenting a seminar titled Improving the Energy Efficiency of Comminution. Be careful on what you wish for. So please, let's give a warm welcome to Steve.
Very much. Yes. Thank you very much. Good morning, everybody. Everybody can hear, I take it? Yep. A somewhat cryptic title. Hopefully by the end of the seminar, you'll understand exactly where I'm coming from. I've used the first few slides before. Those of you who have listened to a number of my talks, but I want to repeat them because it helps set the scene for what comes next. These are just four quotes from public sources. There are a lot more, but they have basically the same content. First one from the US Department of Energy, that the mining industry is the most energy intensive, and it reckons about 11% of total global energy use is associated with that particular industry. The second one, very prestigious journal, Nature Geoscience. This particular paper, greenhouse gas emissions were equivalent to approximately 10% of the total global energy-related greenhouse gas emissions. Comminution is damned by association, as comminution accounts for a large chunk of mining energy use, and there's a couple of quotes, one from Mining Technology, which has a very big readership, 55 million. 56% of the mining sector's total energy, and the last one from an Elsevier publication, 4% of electrical energy consumed by comminution. Now, most of this is hyperbole. Be that as it may, these statements have significantly influenced decision makers around the world, not least people in government, senior researchers, to look at this area because it's been highlighted, at least according to these articles, as an area that accounts for a huge amount of greenhouse gases. However, if you take the trouble to do the calculations and then you do them again another way, and then you do them again another way to cross-check, you end up with the following numbers. So this is the electricity consumption in mining. And if you look at the blue figure, 140 terawatt hours is what you end up with for comminution. Global electricity consumption currently, when I say currently, that's probably last year's, the most recent figures, is 26,000 terawatt hours. So comminution as defined here in the mining industry is 0.5%. It's not 4% as claimed by many researchers. Now, I've fallen into a trap here. It's the first trap I fell into. Mining industry. I suppose I've always worked in the hard rock mining industry and thought that's all there was to the mining industry. Well, it's not. The broader definition there is hard rock plus non-metal valuables, and I've taken that from the literature, such as, for example, coal, stone, aggregate, and sand. That's the quarry industry. The quarry industry is huge. And clays, lime, that's lime for water treatments. And there's a host of smaller sort of boutique, if you like, bits to the mining industry. And if we include that in our definition, we end up with a somewhat larger figure, 245 terawatt hours. And you can see there, it's quarrying that mostly accounts for that 105 terawatt hours there. We've now got comminution up to 0.9%. Still nowhere near our 4. I mean, in fact, there are people that say it's even bigger than 4. So the second trap I fell into with this is that, of course, comminution is not the exclusive domain of the mining industry. Comminution you find absolutely everywhere. And if you look at comminution as a process, we find that only 39% of it actually is in mining. And in hard rock mining, it's only 22%. There's cement, a monstrous figure as far as comminution is concerned. Coal pulverizing, we're going to talk about that later. Flour milling, would you believe? Well, you think of how many loaves of bread are eaten around the world every day, or rice flour. Processed foods use huge amounts of ground rice flour or wheat flour or maize flour, and it costs comminution energy. But we're still only 2.5%. So what about greenhouse gas emissions? Well, at the end of the day, how much electricity comminution, and we're going to talk about comminution, I'm going to drift away a little bit from mining, from comminution. The amount of electricity consumed is to a large extent irrelevant in the context of global warming. It's the greenhouse gases that are emitted from the generation of that electricity. That's the number we need to know. The current figure for conversion of terawatt hours of electricity generated to greenhouse gas tons is that figure there, 500,000 tons of CO2e. What does that CO2e mean? That's carbon dioxide equivalent. So it contains both carbon dioxide as a gas plus NOx's, SOx's, and methane. Methane is a really, really big one. And there are conversion factors, and there is some controversy concerning the conversion factors from those gases to the equivalent carbon dioxides. So it's not just CO2, it's the equivalent CO2. And if you take, and where that 500,000 tons comes from, if you look at the global electricity supply industry, and for 1 year, you add up how much they consume, and then you calculate how many tons of CO2 is pushed out the stack from generating that electricity, you get a figure of 500,000 tons per terawatt hour. Country to country, of course, it varies. If you had a 100% sustainable electricity supply system, let's say it was all solar and wind, that figure would be not 0, but it would be very, very, very small. So I'm looking at global figures only here. So what does it look like when we now consider CO2? The, again, current, at least last year's approximate emissions, 55,000 megatons of CO2 emitted per year. And for comminution, we end up with 318.5. So comminution as a process, 0.58% of the total global emissions of CO2. So again, not to belabor the point, nothing like what we see in a lot of literature. And if we go up to hard rock mining, which mostly is where my experience has been in, it's 0.13% of greenhouse gas emissions. Now, although it's relatively small, in my view, it's relatively small. That doesn't mean to say, and I'm certainly not saying, that we should therefore ignore it and not do our very, very, very best to try and reduce it. How can we do that? Of course, the most obvious one, and it's the subject of quite a few research programs around the world that people here have worked on different ways of comminuting rocks, trying to find a way of reducing the amount of energy that comminution consumes. So we're going to look at how we can improve comminution energy efficiency. What is, and we have to start somewhere, what is comminution energy efficiency? Well, once again, I've gone to the literature and I've extracted this first quote here. There are quite a few of them that more or less say the same thing, slight changes to the numbers. Comminution is inherently inefficient. Often see in literature, it is well known that comminution is inefficient. Everybody knows that. I hate it. If I'm an examiner, the first thing I do is cross that out, but give me the reference. That's sometimes quite difficult. This particular one, as I said, is fairly typical. 95% of energy consumed by heat, noise, and mechanical losses, only 5% being consumed to break the rock. And if you look across a broad range of literature, you'll find variations on that theme, anything from 0.1%, so not 5%, 0.1%, up to as much as 25%. That might, to some of you who are not in comminution, be a bit odd. I mean, we've been at this game for a hell of a long time, and we still don't know or can't agree on what the actual energy efficiency is of comminution. Back in 1992, while I was at the JK Centre, I became interested, one of the many things I became interested in at the JK Centre. And having had a look at the literature and seen what those people were saying, and these quotes are from very, very, very prestigious and well-known people. And in those days, I believed everything that was in the literature, particularly from particular sources, professor this or professor that, must be right. So I've got to think, if, given that example I gave, if 95% or 80% or 75% of energy goes into comminution comes out as heat, why don't I do a heat balance around a comminution circuit? Work out how much heat comes out. I know what goes in because I'm measuring power draw, and that was one of the things I was into in 1992, doing my PhD thesis on power draw. So I thought, well, if I do that, work it all out, there's going to be a gap somewhere, and that gap in the energy balance is going to be comminution. Maybe. So Red Dome, some of you will remember Red Dome. It is now no longer. See a hand up there, I know very well. He would have remembered Red Dome. Tim almost certainly does. Very good mine. I went to site with Doug Brown in 1992, who was the head of the lab here at the JK, and Bill Finch. Bill was a master's thesis flotation guy, and we all went to site. We persuaded, it was P9, we persuaded the management there that we could drop the mill, so stop the SAG mill, empty all the contents, weigh all the balls, weigh all the rock. It was about a couple of 100 tons. It was the second time I'd done it. It was bad enough the first time. It was even worse the second time. We were trying to develop the variable rates model, which was the variable rates ag and SAG mill model. And to get a really good handle on the parameters in there, you need a load size distribution. Anyway, to cut a long story short, the management says, yes, go ahead, do it. And I thought, well, while I'm there, I'm going to measure the temperature of all the streams around there. I can measure the power draw, because that's what I was there for. I can get a mass balance around there. I should be able to do a heat balance. Fantastic. So from a physics viewpoint, what do we need to do for a mass balance? Well, first of all, we've got heat loss. 3 types of heat loss. We've got conduction, radiation, and convection are the 3 ones that we need to consider. The conduction part of it is the one that's most important in terms of transferring heat into the slurry, which is I was measuring the temperature of. Radiation, that's from the surface of the mill, which should heat up. And convection, of course, the mill's going round and round and round, so there's convection transfer. Mechanical losses from the motor and the gearbox. Well, one of the good things about doing a drop of a mill, you empty the mill. When you start it up, you start up on what's called no load power. So you get a very, very good idea of what all the mechanical losses are. It's not 100% accurate, but it's a damn sight better than estimating it. So we knew we were going to get that. And then noise, well, we assume that to be negligible. Randolph's an expert in noise, so I would defer to him. But having a look at noise and the power intensity of noise, for example, a loud rock concert, you'd have about 1 watt per meter squared as the sound intensity. So in terms of magnitude of energy, it's relatively small. I had no way anyway at the time of actually measuring it. So that was put to one side as being, can't measure that. Let's assume it's small. All right, conduction. A little bit of physics, high school physics, it should be for most of us. If we look at conduction, very simple equation, flow rate, M times C, which is the specific heat, times delta T. Interesting, you may or may not know this, the specific heat for water is huge by comparison to a rock. You can see it there, 1.16 compared to 0.19. Water is a heat sponge. It soaks up huge amounts of water compared to rock. So that's the first equation we've got to consider. Radiation, the black body radiator equation is that equation less the emissivity. If the emissivity is 1, you have a black body radiator. Well, most mills are painted, and the Red Dome mill was painted, and paint has an emissivity of about 0.95. Sigma is the Stefan Boltzmann constant, and we now need the temperature difference between the mill shell and the ambient, which we knew. Last but not least, convection. Most convection equations, H is for still air and still motion of any metal parts involved. And you need an empirical equation, because that's all you've got. That's the empirical equation there for what's called assisted convection. So when there's relative motion between the parts that you're interested in from a convection viewpoint, then you need something which relates to the velocity, and that's what that V is there. So that is that figure there of 34 times 10 to the power of -3 kilowatts per cubic meter degrees C is for a mill moving in air. And I knew the speed of the mill, so I knew what V was. Okay, so I've got all of that. What were the results? Rubbish, actually. It was back to the drawing board. Couldn't make sense of the results at all. And we're going to go back to this later, not least because this was actually one of the first slip energy recovery motors in the mining industry anyway. And I had untold problems on the mine site to actually get an electrical engineer that could sign off and say this was the actual power draw of the mill because of the slip energy recovery system. So there was a big question mark on that. And of course, that was the major input to my methodology. And if you don't know what's going in, well, you can't do a subtraction at the end to work out how much was comminution. So I decided to let that idea lie dormant. I had much, much better things to do at the time. And dormant actually meant another 25 years it stayed there. Basically, those results got stuck in the bottom of my office drawer. Where they finally went to, I've got no idea. But I do remember the conclusion, and we're going to come back later to that. I had an opportunity of doing this again a few years ago with maybe some reasonable additional insights into what on earth was going on. So here is a schematic of the circuit we had a look at. And you can see here we have our mass flows. In this particular case, it was 1,456 tons per hour. Water input, 630. Power draw of the mill, 11 megawatts. And we measured a temperature increase across the mill of 10 degrees. So in this particular case, that's how much the slurry heated up. Measure the temperature of the mill shell. And when we did our balance, these are the figures we got. So if we look at up here, 11 megawatts is what's going in, or at least that's what's metered going into the motor, which drives the gearbox, which drives the mill. Conduction worked out to be just over 10 megawatts, radiation fairly small, and convection a little bit greater. Mechanical losses here I had to estimate because there was no way they were going to let me stop this mill, empty it, and measure the no-load power. So I'd got some equations from my PhD thesis from looking at a number of mills where they did let me empty the mill and get no-load power. So I used that approximation for the no-load power as my estimate of the mechanical losses. Balance, 210 kilowatts, magic figure. 1.9%. So have I found the magic number? 1.9% is the efficiency of comminution. Not at all. From a statistical viewpoint, you're lucky doing a mass balance or a heat balance to get within 5%. Most of the time, you're lucky to get within 10%. So all this really did was prove that there was no statistically significant difference between what went in and what came out. Couldn't prove it. And interestingly, the reason I said that 1992 Red Dome thing was rubbish is that I actually got more energy out than I put in, which is, that's why I decided, no, this is rubbish. This is an energy generator. And clearly, again, because of that 5–10% error, it was about 5 to 10% extra energy I found from somewhere. Again, all it was saying was there was no statistical difference between input and output. So what does this mean? Anybody have any idea who these people are? There. I thought if anybody in this audience, if Peter's going to come along, Peter Munro, my good friend who would know, well done. One of them is Peter Kelvin. They would know what's going on here. They would immediately pick up on what on earth was going on. You may not have heard of Rudolf Clausius, but Rudolf Clausius and Lord Kelvin are both generally regarded as being the first to state the first law of thermodynamics in the way that we see it in modern times. And that was in 1850. They didn't do it in isolation. In my view, most of the heavy lifting was done by Carnot. That's Carnot from the Carnot heat cycle. Sadly, he died, I think he was 36 when he died, and he died before the first law of thermodynamics was, in fact, published in that form. Posthumously, people went through his notes and they found he'd actually, he'd almost got there from his notes. Excuse me. My hero, however, is James Joule. And why I say he's my hero, well, let's go to the next slide. First law of thermodynamics. This is one way of stating it. There are a number, but this is the one I think most of us are familiar with. Energy can neither be created or destroyed, but it can be transformed from one form to another. Now, the reason that James Joule is my hero, and I can still remember at high school doing physics, learning about the mechanical equivalent of heat. And for me, that was a revelation. Together with Heisenberg's uncertainty principle, which also sticks in my mind, was another revelation, which probably goes to show what a nerd I must have been in those days to be excited about that sort of thing in one's teenage. But nevertheless, it was there, mechanical equivalent of heat. Brilliant. And in particular, it was James Joule's experiment, which is what I love. It was absolutely brilliant experiment and is absolutely relevant to our example here of milling. This is a picture of what he did. He had a drop weight and he dropped the weight, and that weight transferred potential energy into kinetic energy. It made this paddle in that water move and it heated up the water. And he did it again and again and again. And he worked out that mechanical energy was totally transformed into heat. Brilliant. And if you think about a mill, what are we doing? We are transferring motion into heat. All the motion that goes in, all of it comes out as heat. Every single BTU, joule, call it whatever you like, it all comes out as heat. I particularly like this because as some of you may know, the drop weight tester was invented here by the JK. Substitute that for a drop weight tester. I'm dropping the weight. I'm not stirring up this. I'm breaking a rock. Same thing. All the energy comes out as heat. So what does it tell us about energy efficiency? Well, actually nothing, unfortunately. It was a stupid experiment in the first place. I thought it was a good idea at the time, famous last words, but it was not such a crash-out idea to get to comminution energy efficiency. But it does show us that comminution is a very, very efficient heater. If you thermally lag that mill shell, there's a good chance you get up to about 95% efficient heater. That is brilliant. That is just way out there. And of course, what that does and what we see does is it heats our slurry up. And I measured 10 degrees. It's typically between 10 and 15 degrees increase in slurry temperature across the mill. It obviously depends on how much you put in. If you have a very hard rock, you have a much higher kilowatt hours per ton, so the temperature increase is much higher. For dry grinding, you can get up to 100 degrees C increase in temperature of the ground product. Why should it be that much higher for dry material? It goes back to that specific heat difference between water. Specific heat is really high. We no longer have that massive heat sink of water. All the energy goes into heating the rock. So you end up with a very, very hot rock. Any of you, I mean, Mike Daniel's not here in the audience, but I can remember Mike, who was a student here. We had, I don't know if we've still got it, a little HPGR machine down in the pilot plant. HPGR machine, you can change the amount of pressing force. And he was experimenting and putting in huge amounts of pressing force. Well, he burnt his hand, I think. It was so hot, the product that comes out, you can't touch it. It is so hot. So it's definitely a real effect. Again, well, so what? Well, going now back to improving energy efficiency, because the amount of energy you put in gets converted to heat and comminution is a heater. If we improve comminution energy efficiency, we're going to reduce the amount of energy that the comminution machine uses, and therefore we're going to produce a cooler product. A more efficient comminution is a cooler comminution process, and that has significant downstream consequences. Let's go back to our comminution energy table and look at where comminution energy is consumed. And let's start with coal pulverizing. Yes, this is for kindergarten grade kids to illustrate what a power station layout should be, but it serves my purpose. It's just something off the internet. I wanted it to look really, really simple. And we can see here pulverizing of coal. Coal, by and large, in coal-fired power stations is always pulverized. It's ground down to about 75 microns, and it's injected into the boiler. It's almost a gas at that point. What's not put in here is heat of comminution. So that grinding mill is putting hot coal into that boiler. Now, all a power generator is a machine that converts heat in to electricity out. So if we now start mucking around with the heat of comminution and ending up with a much more efficient comminution machine, we'll end up by feeding it cold. I know I'm exaggerating it, but I want to make that point. It's cold coal. And what that does is upset the energy balance here. If we did nothing else, what it would do would be drop the temperature in the boiler. If you drop the temperature in the boiler, you will not generate as much electricity. So we've just saved electricity in the comminution process, and we've now lost it in power generation. Now, you might argue quite rightly, surely there are waste heat streams here that we could tap into to compensate for the fact we've now got cold comminution. And this is a somewhat more complex view of a power station. And in fact, that's already what is done. All this over here is all about capturing all the waste heat. Here's our pulverizing mill here. And what we should have put in here is heat of comminution. And where I've got that red oval there, that's the current system for heat exchanging, which heats the air up. So all the waste heat currently in a very efficient, and we're looking now at ultimate efficiencies. So here we've got the most efficient coal-fired power station in the world, let's say. It uses up all the waste heat, and now we go and subtract our comminution heat. The net result will be not as good as you thought it would be. Is it a one-to-one loss? Probably not. Almost certainly it won't be, but it needs to be considered before somebody jumps in and decides, I've got this wonderful new comminution machine to reduce the grinding energy in coal. It has far-reaching consequences. Okay, let's go to the big one, cement. 48.7% of all comminution electricity goes into the cement manufacture. And here, once again, is a very, very simple schematic of a cement production. For those of you not familiar with cement, the basic equation, and there are lots of them, this is highly simplified, it is the conversion of calcium carbonate into calcium oxide and CO2. The cement industry is a monstrous consumer of thermal energy, converting usual units. I mean, we mostly think of heat in terms of gigajoules. I've converted it to kilowatt hours per ton down there. So that's not electrical energy. I've just simply changed the units because I want to compare it to the electrical energy that's used. If you look down there, ballpark figures, 1,000 kilowatt hours per ton is used to produce cement. That's the dry process. Wet process, you can increase that by 50%. Electrical energy consumption is of the order of about 10%. And of that, between 65 and 70% is grinding. Where's grinding? Well, the raw material that goes in is ground, and it's then fed into the clinker burning stage. Temperatures there up to 2000 degrees C. Also, the final cement grinding stage also consumes electricity. Now, having already said what I said about coal grinding, I don't need to tell you where I'm going with this. Huge amounts of heat are generated. And again, if you look at the most efficient cement industries, and there's a huge effort being put in to recover through waste heat generation as much of that heat as we possibly can. So this is our waste heat generation system embedded in our cement works. Raw grinding here, there's the kiln, there's our coal mill, there's our final grinding there. All those heat flows are gathered together in the most efficient cement industry to generate electricity. 65 to 70 kilowatt hours per ton is going into comminution. So once again, if we end up with the magical cool comminution, we will need more energy to be pumped in, raw energy, which means more CO2 to generate and produce our cement. Let's go back to our other comminution candidates. Now, quarrying and flour milling, I've looked at those, and from a temperature viewpoint, I can't find anything there that suggests that if we tamper with the temperature of the product, be it flour or sand or quarry rock, it has any effect whatsoever on the downstream process. As far as I can see, they're not processes one needs to worry about. What about hard rock mining? Well, that's an interesting one. Let's go back to what hard rock mining is composed of in terms of those valuables that are ground down. Copper, iron, and gold are the big ones. There's about 80% there. Most of that iron is not direct ship ore. I mean, that's the stuff we've got lots of in Western Australia. Dig it up out of the ground, put it on a ship, and off it goes. It's mostly low grade. Low grade typically, at least in Australia, uses mag separation. I'm going to knock that one off first of all. Once again, I can't find anything in the literature which suggests that the mag sep process is in any way affected by the temperatures, at least within the region that we're talking about here. Flotation, however, is the dominant process in nearly all of the other processes apart from gold, and gold is CIP and CIL. Even in low-grade iron ore, if you go to China, flotation in particular is quite common. So there's also flotation in iron ore. Now, what I know about flotation and CIP and CIL is decidedly dangerous. So I'm in no way an expert in this. And what I decided to do was just pick the eyes out of some literature. I did a literature search, and I just want to share with you some of the more interesting ones that relate to flotation and CIP and CIL with respect to temperature. This is a really interesting one. I know we have some people here with South African origins. This graph comes from a pyrite mine in the Free State. And the management team there noticed that during the year, pyrite production, that's that one there, went down, and its lowest was basically in the middle of winter, and then it went up again as it went back to summer. And the black line there is the temperature that goes with it. And they asked a team of flotation experts to have a look at it, and you will recognise, sorry, wrong way, you'll recognise two of them, Cyril O'Connor and Rob Dunn. And they wrote a really interesting paper. It was published in the South African Institute of Mining and Metallurgy. And this is one of the graphs from their paper, effective temperature on the rate of pyrite flotation. And that's the flotation rate constant on there. So they did experiments just in the lab to see if they couldn't reproduce what was happening on the production level. Their recommendations to overcome this seasonal variation: increased residence time and or higher impeller speeds, or heat the pulp up. They all require more energy. So in this particular case, if we were to have a cooler comminution process, this suggests we would significantly impact in a negative way the flotation rate of pyrite, and in this particular case, in particular mine, their production would decline. This is just a quote from another paper. It was published last year. To be honest with you, I said how much I know about flotation is dangerous. Half of it I just did not understand. So I thought I'll go straight to their conclusions and recommendations. They were looking at a copper lead zinc ore, and that's the name of the paper. And these are the of the researchers that were doing it. And to quote, pulp temperature between 20 and 60 degrees C, and they're the temperatures we're talking about in comminution circuits, affect flotation of this particular copper lead zinc ore. And they showed that pulp temperature was the most significant parameter affecting flotation performance. And the grade increased with all of those with increase in temperature. What was interesting, and I should have picked up on it, if we go back to that pyrite paper, Cyril and Rob and D'Souza did some experiments looking at viscosity, because they were interested in the extent to which viscosity of the pulp was influencing flotation performance. And they measured the effect of temperature on viscosity, which those of you who are into viscosity will be well aware of the effect of temperature on viscosity. Lower temperature, viscosity goes up. Well, that, of course, affects pumping. So if you have a cooler slurry, you will have a more viscous slurry. And here is a schematic of what viscosity does to pumps. The black line there is water, and the dotted line there is a liquid with a higher viscosity. And you can see that higher viscosity means loss of head, lower efficiency. And if you wanted to keep the pumping rate the same, you would have to add power to the system. So slurry pumping's everywhere. It pervades comminution circuits. So there's another example of where the wheels might not quite fall off, but they'll start to wobble if you're not careful. What about CIP and CIL? Well, this is a really interesting PhD study, and it was done, it's not that long ago. Some of you might know the Fort Knox mine. It's in Alaska, and this basically picks up on that pyrite mine I mentioned, where they found seasonal variations in production. And of course, Alaska, some of us have worked there, it's bloody cold. And there in midwinter, their slurry temperature went down to about 10 degrees C. And they noted that gold production was less. And so this PhD student, he got his PhD, did a modelling, basically it was all about modelling. And he collected quite a lot of data. And this is one of his data sets. Gold recovery here on the y-axis and temperature along the x-axis. You can see here, that's their winter temperature. And in summer, their slurry typically goes up to about 25 degrees C. He extended the ranges to see whether that gold recovery versus temperature relationship continued, and it did. And one of his conclusions were, to put it into perspective, that on that mine, a 15 degrees C drop in slurry temperature due to the weather, substitute that, our cool comminution has had that effect, cost their mine 1 kilogram of gold a day. Well, at current gold prices, that's $45 million a year. Now, I know that's got nothing to do with global greenhouse gases, but if you wanted to keep your production up, you can start to think, what have I got to do to counteract that drop in temperature? Heat the slurry up? Well, that's probably not feasible, but you're looking at increased tankage, more power, let alone the money aspects of it. So what are the conclusions? Well, first conclusion is comminution is a very, very efficient heating process. Improving comminution efficiency, if we can find ways to do it, will result in cooler products. First law of thermodynamics dictates that that will be the case. From what I can see, there is a temperature effect on downstream processes. It may not be consistent. It may well be that there's, in some cases, it has a negative effect, in some cases a positive effect, in some cases have no effect whatsoever. But predominantly what I've seen is that those processes work less well at a cooler temperature. So the impact of increasing comminution efficiency, and this is really pitched at researchers out there, just beware, you really do need to look holistically at what's going on to see whether what you're doing isn't going to end up with grief, or at the very least, a null result, which is, well, we've just basically put all this effort in and we've gone absolutely nowhere. It's a waste of money and it's a waste of time. And just to end, some of you will know that one of my favorite aphorisms is no such thing as a free lunch. Well, that is, in layman terms, the first law of thermodynamics. And that basically is what we've been talking about today. Thank you.
All right, thank you very much, Steve, for a very interesting talk and presentation. So I'm going to open for some questions on the audience. Anyone? All right.
Ray Koenig. I went to Melbourne Uni, and we were fortunate enough to have the ore dressing division of the CSIRO right behind us.
Yeah. And
we did all our pracs at the ore dressing division. And I think it was Trahere. He had us crush quartz and measure the increase in surface area of the quartz and try and calculate from the bonding of the silica what the energy efficiency was. And we came out with a figure of just over 1% putting it through a crusher. So that's a different approach to looking at it, but it ties in with a few of the figures there. It's not we always knew it wasn't a very efficient process, and ball milling would have been even less efficient because it's a probability thing. So, and that's another alternative approach, I guess. Did you think about using that approach, or?
I have spent quite a few hours and quite a few days and quite a few weeks trying to get my head around those experiments, because a number of researchers have done exactly the same thing. And it comes back down to something called surface free energy. It's a bit of a nebulous thing, surface free energy, and it is very relevant at the atomic level. And in the end, I gave up because to me, the biggest fault of all those researchers is that they related surface area to surface area that you can see here. Whereas when you go along that bonding route, what you're actually really interested in is the atomic surface area, which is orders of magnitude greater. So when you do your equations, you get the wrong answer. And it's a bit like the, I don't know whether you've heard the, is conundrum, not conundrum, but anyway, what is the circumferential length of Australia? Well, it depends on the resolution at which you measure it. If you measure it to within 1 kilometre, you get one value. If you measure it down to the nearest millimetre, it is orders of magnitude greater. It's that resolution. And that's the problem I had with those surface area measurements related to atomic bonding. It's that theoretical energy of bonding. You can actually measure it, but it comes back down to what is surface area. And any of you have looked at under an electron microscope something which looks like it's a nice smooth surface. Well, it ain't. It's basically all over the place. And I think that's the problem with those, in my view, with those calculations, because they're the ones that tend to give you, and 0.1%, that 0.1% came from experiments. I know Len Austin quoted, I don't think Len Austin did, it's Professor Len Austin, did the experiments, but he quoted that in one of his papers from years ago. He was one of my, you know, before I started to become a cynic and a skeptic, and don't believe anything that anybody tells me unless I can actually, you know, I should have been called Thomas, you know, the doubting Thomas. I'm hopeless nowadays. I used to believe all of that stuff. And Len Austin, his thing stuck in my mind and drove a lot of us on. Wow, the comminution is absolutely appalling. You know, there's this massive prize there. It was only 0.1%, you know, or 1%. So I'm rambling on a bit here, but yes, I have looked at that and discarded it as being probably not valid. I much prefer the approach that I think Furstenau and also Professor Schernert did, which was say we need a benchmark, and the benchmark is single particle breakage by a rigid device. And that is the best that we can do in the way that we comminute now. That becomes our benchmark, and everything else compares to it. And we knew from the paper that Tim I and Jan Anderson published about crushing, if you compare crushing power to the power that a drop weight tester would need to do the same thing, you have an offset of about 25-30%. So you use 25-30% more energy in a crusher than a single particle. And then, of course, HPGRs use a bit more. And milling, there's no doubt, milling is the worst of the lot. There's no doubt it uses more energy than those other processes. It begs the question, can we do something other than breaking a rock by hitting it? I don't know.
Thank you, Stephen, very much. To follow up on that particular question, measuring accurate surface topography is very much a doable thing nowadays using atomic force microscopes that can give you surface topology down to an angstrom.
I realise you can do that, but talk to the researcher. I mean, I'm actually not too interested in following that approach, because to me it's an interest from an academic viewpoint. I realise that you can. I have actually studied that as a way of looking at surface area. I know we can do it now. Maybe it needs some bright PhD student to go back and revisit that and use that sort of information that we know we can now get.
Perhaps that would be a good way to start to go back to the basics and start looking at the fundamentals of energy efficiency when it comes to estimating breakage energy. So, yeah.
Thanks so much, Steve. We've been doing some work on modeling cyclone milling circuits with soft sensors. And one of the things that we found was that we had to incorporate temperature to be able to model the classification efficiency using the cyclone models, because there was a big difference between summer and winter again. So I was wondering if you had also seen such a thing in classifiers.
I haven't. It wasn't something, to be honest with you, with my literature research, it wasn't something I looked at, and it's not, and it's not something I've specifically looked at. I mean, I do recall the work that Tim and Frank Scher did sort of years ago, looking at rheology around milling, and I think, did Tim, correct me if I'm wrong, did Oscar Castro with his work, I think he started looking at rheology, I think, which would have been impacted, of course, by a temperature. So I'm not surprised now, just thinking it through, I'm not surprised that that's what you're finding. So I suppose, to cut a long story short, yes, I have come across it, but I can't remember all the details. And I know there is some historic work here that might be of some sort of use in the work that you're doing there.
Thanks. Thanks, Steve. That was really interesting. Very interesting, I thought. My question is that your estimate of I guess energy and emissions associated with comminution is really significantly lower than the published figures that you were referring to at the very start of your talk. Did you in the course of doing your calculation, did you work out where the other authors who published those higher figures actually went wrong?
I don't want to say they went wrong, because I think that would be unfair. There were two categories, and it's a particular pet hate of mine. There was the one category that would make a reference, and that person made a reference to somebody who made a reference to somebody who made a reference to somebody, and I went back to that first reference. That wasn't what he or she said at all. It's basically Chinese whispers. And the other category, and I have to say in some cases it was mischief, because there were a number of papers that when I started reading them, the headlines would be, mining industry, greatest polluters on earth, and blah, 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 blah. And as you read further down, footnotes, mining includes iron and steel production, and all the rest. And I know iron and steel production is a massive emitter of global greenhouse gases. It does not belong in mining, in my view. So they had not defined mining up front. If they'd said mining and metalworking and so on, not a problem. And that's where a lot of the figures came in. The other area, and again, it comes back down to our definition of mining and what we include. If you look at coal and coal's emissions, the gas emissions, methane gas in particular, from disused coal mines, once you add that up and you lump that into mining, you end up with an alarming figure. Part of it is because nobody can agree what the CO2 equivalent is of methane. Methane breaks down in the atmosphere. So they come out with these figures of a 5-year, 10-year, 25-year, 30-year rate. And if you wait long enough, it's gone. And basically, it's zero CO2. In the first year, it's really high. And different authors would use different figures depending on what the intent was of their paper. And unfortunately, more often than not, the papers were always biased in one direction, whether it was to show how fantastic and important their research was, or, and I've been in that game before of getting research money, look, this is really, really, really important, and I need your money to go and do some research. So those are the main categories I found, because I mean they have to come from somewhere. It wasn't well, apart from those that keep on going back and back and back and back and back, wasn't sort of plucked out of thin air. So those were the major cases.
We have an online question from Farhad. I'm just going to allow him to talk. Farhad, are you there?
Hello, can you hear me?
Yes, thanks.
Hello, everyone. Hello, Steve. Thank you
Farhad.
very much for your great insights. I just have two quick questions. So, based on research, under compression, the energy efficiency can range between 5 to 10%, and under, uniaxial tension or tension strengths, it can get to 66%, right? So this, to me, means a more efficient braking technique could be or can mean cooler process, right? So first, I want to have your comment on this, because in my mind, maybe we need to search for new solutions or new techniques instead of impacting or maybe compressive techniques. And the second question is, we can make a hypothesis here that different ore competences or different ore types should release different heat levels, okay? So I'm also seeking your feedback on the impact of ore variability on this process or possible solutions. Maybe it could be a future research. Thank you very much.
In answer to your first question, Farhad, breakage under compression, and maybe I misunderstood you, breakage under compression takes a lot more energy than breakage under tension. You can see this quite clearly if you compare UCS, which is an unconfined compressive stress number, and it's a measured number, and you compare it to a point load index, which is pure breakage in tension. The energy of the breakage in tension is much, much lower. Most of our comminution devices, although the motive force is in a compressive direction, the deformation of the rock is such that then generally all or most of it breaks in tension anyway. So most of our comminution devices, in particular crushers, are almost exclusively breaking in tension. Interestingly, HPGRs, although their overall energy efficiency is better than milling, they're not as good as crushing, because in high pressure grinding rolls breakage, there is a significant element of compression breakage because of the constraint within the gap. So it's not as good as crushing, but it's a lot better than milling, which has all sorts of other problems, which I'm not going to go into. So I'm not certain if I've answered that first question for you. With the second question, to be honest with you, I'm not certain whether all variability is other than different ores will require different amounts of energy input and therefore will heat up differently. The variability within an ore type is going to show you fluctuations in temperature. Yes. How much? I don't know. Probably not a lot, because the big driver is the kilowatt hours per ton across the mill. And by and large, mines try and keep that as constant as possible. So, I mean, Bill might come back to me now and say, no, Steve, you misunderstood, and pose the question again, because I wasn't quite certain about where you were going to in that second question.
So with the first question, actually, the numbers I provided, 5 to 10% compression and up to 66% for uniaxial tension, I mean actually energy efficiency. What I mean is energy efficiency of tensile, breaking rocks through tension could be much more efficient than compression. That's why maybe we can revisit how we break the rocks in future comminution equipment. This is the first one. And with the second one, actually, you quite answered the question, right? I believe what I mean actually the difference between the heat levels that can generate from different rock types, and whether this is worthy to consider, or maybe what I mean actually, depending on the ore competence level, maybe we can adopt a more efficient, maybe for some rocks which are less efficient, we can break them in like tensile. For rocks which are softer, maybe compression can work, right? So I mean that tuning our approach based on the rock properties. This is what I meant.
I mean, I don't ever want to say it's not worth looking at anything, because that's you know, I think as researchers we should always be looking at stuff. So I certainly wouldn't say no, it's not worth looking at it. Just to go back to your first question, I think I did answer it, and the fact is, just to reiterate, most of our comminution machines already break rocks under tension. That's their mode of breakage. So the extent to which we can do any better than that remains to be seen, other than where one concentrates the energy. And to some extent, I suspect that's what's happening with microwave pulsing and electroshock therapy, I call it for the other technique, is being able to concentrate that energy at the flaws inside the rock. So you don't actually have to deform the entire rock to get to the point where you end up with tensile breakage. You'll concentrate that energy in a localized position, and that's where you save the energy. How on earth you do that is another matter. And of course, one of the things one must remember, and it's something, and I'm really going off the reservation a bit here to some extent, when one looks at things like microwave pulsing to weaken rocks, I have seen a couple of papers. When they looked at the downstream effects and found that they reduced comminution energy, they failed to include the amount of energy they put into the microwave machine. And when you added the energy of the microwave machine, guess what? There's no free lunches there either. So again, one must be careful.
All right, I think that's
you.
all we have time today. So there are a few more online questions. So please feel free. Sorry, just reach to Steve afterwards, and let's please thanks again, Steve, for his presentation. So next week we have Simon Schuh from the Geological Survey of Finland talking about the purple transition, the start of a possible solution for the energy transition. So hope to see you all.